In this section, we will see what is linear congruence. So far actually we studied relation like A congruent to B modium, which involves only integers. Now we will see congruence relation involving variables like 3x congruent to 4 mod 5, x square congruent to 1 mod 8, x square plus 1 is congruent to 2x mod 5 or 6, likewise. And we are focusing on a particular type of congruence involving variable, that is of this type, which involves first degree variable. So a linear congruence is a congruence relation in the form Ax congruent to B modium. Now we can see that a solution to this Ax is equal to congruent to B modium means a value for x from z, say x naught, such that Ax naught congruent to B modium. If there exists such an x naught in Z satisfying Ax naught congruent to B modium, then we say this x naught is a solution to the linear congruence Ax congruent to B modium. For example, consider the congruence 3x congruent to 4 mod 5. Now it is very clear that when x is equal to 3, say 3 into 3 is clearly congruent to 4 mod 5. Because 3 into 3 is 9, 9 minus 4 is divisible by 5. And therefore 3x is equal to congruent to 4 mod 5 has a solution 3. But if we take another congruence, linear congruence like 4x congruent to 1 mod 2, it has a solution if 2 divides 4x minus 1. But 4x minus 1 is always an odd number for any integer x. And therefore 2 actually does not divide 4x minus 1. Therefore, we can say 4x congruent to 1 mod 2 has no solution. So some of the linear congruents may have solution or solutions and some may not have. Now we will see under what condition a linear congruence can have solution, how many solutions it will have, etc. we will be seeing. To find solution to a linear congruence Ax congruent to B modium, we are going to identify the linear congruence Ax congruent to B modium with an equation, linear Diophantine equation. You can see that there is a connection between linear congruence and linear Diophantine equation. We know what is a linear Diophantine equation. An equation in the form Ax plus By is equal to C is a linear Diophantine equation if the coefficients A, B, C are all from the set of integers or are integers, and the x, y unknowns are also integers. Such an equation is called a linear Diophantine equation. A linear equation in the form Ax plus By plus C equal to C with the coefficients A, B, C set of integers, and solutions we are expecting only from the set of integers. Now, how to write linear congruence Ax congruent to B modium in the form of a linear Diophantine equation? So that is what we first see. Ax is congruent to B modium if M divides Ax minus B. That is, Ax minus B is a multiple of M. Usually we write Km, but here we are writing Ym since X is an unknown here. So we should bring here also another unknown. So Ax minus B is equal to Ym, or you can, other words, you can write as Ax minus My is equal to P, which is a linear Diophantine equation, because its solution we are expecting integers, and this A, M, B, the constant coefficients are also the set of, from the set of integers. So any linear congruence Ax congruent to B modium can be regarded as the linear Diophantine equation Ax minus My equal to B. So this linear congruence has a solution, or it is solvable if the linear Diophantine equation 1 is solvable. And we know what is the condition for a linear Diophantine equation to be solvable, and how to find a solution to a linear Diophantine equation. So before going to solving linear Diophantine equation, let us think of a solution to a linear congruence in the form Ax congruent to B modium. If X naught is a solution to Ax congruent to B modium, then Ax naught is congruent to B mod M. Now X naught, if is its solution, then we have X naught congruent to B modium. Now suppose there is another integer x1 which is congruent to X naught modium. Then we can see that Ax1 is congruent to Ax naught modium by using some of the properties of congruence relation. And since Ax naught is congruent to B modium, and this is congruent to B modium, and that is Ax1 is congruent to B modium. So what we are getting is, if X naught is a solution, that is, if Ax naught congruent to B modium, then Ax1 is congruent to B modium, which indicates that X1 is also a solution to the linear congruence Ax congruent to B modium. So this result establishes that if there is a solution, then there are actually infinitely many solutions, and this X1 is actually is congruent to X naught. So any integer congruent to X naught modulo M is also a solution to Ax congruent to B modium. In general, all the elements in the congruence class of X naught are solution to Ax congruent to B modium. For example, let us take a congruence, linear congruence 3x congruent to 4 mod 5. Earlier we found that x is equal to 3 is a solution to this congruence 3x congruent to 4 mod 5. So you take the residue of modulo 5 which are in the class 3, that is all the elements in the congruence class of 3 modulo 5, which consist of the integers like 3, 8, 11, etc. Similarly -2, -7, etc. are all solution to 3x congruent to 4 mod 5. So since 3 is a solution to 3x congruent to 4 mod 5, then all the integers which are congruent to 3 modulo 5, that means minus 7, minus 2, 3, 8, 11, etc. are also solution to 3x congruent to 4 mod 5. In general, if 3 is a solution to 3x congruent to 4 mod 5, any integer in the form 3 plus 5t is also a solution to the linear congruence. Thus, if Ax congruent to B modium is solvable, if there is a linear congruence Ax congruent to B mod M, if it is solvable or if it has a solution, then it has infinitely many solutions. Then it has infinitely many solutions. But we are not interested in this same solution in the same class of congruence. We are expecting, or we are actually determined to find, or we are interested to find incongruent solutions to Ax congruent to B modium if it is solvable. How many incongruent solutions are there? For example, you consider the linear congruence 9x congruent to 6 mod 12. You can see that 9 into 2, that is 18, is congruent to 6 mod 12, which implies 2 is a solution. 9 into 6, that is 54, is congruent to 6 mod 12. 54 minus 6 is 48, is a multiple of 12, which indicates 6 is also a solution. And 9 into 10 is also congruent to 6 mod 12. It indicates 10 is another solution for this congruence relation. But 9x congruent to 6 mod 12 has different solutions 2, 6, 10. One can verify that all these 2, 6, 10 do not belong to the same equivalence class modulo 12. That is, 6 is not in the class of 2. Similarly, 2 is not in the class of 6. That is congruence class modulo 12. These solutions 2, 6, 10 are called incongruent solutions to the linear congruence 9x congruent to 6 mod 12. So in this section we will be seeing how to get the incongruent solution of Ax congruent to B mod M and how many incongruent solutions will be there. Now we will see a necessary and sufficient condition for the linear congruence Ax congruent to B modium is solvable. The theorem says that the linear congruence Ax congruent to B modium is solvable if and only if D divides B, where D is GCD of A. which is D, which divides B. And it has so many incongruent solutions. That means D number of solutions it has. So this is what we are going to prove. So assume that Ax congruent to B modium is solvable. That means the corresponding linear Diophantine equation Ax minus My equal to B is solvable. And we know under what condition a linear Diophantine equation in the form Ax minus My equal to B is solvable. If this is solvable, if the GCD of A and M, there is AM, divides B. So we have the condition that the linear congruence Ax congruent to B modium is solvable if D divides B, where D is the GCD of A and M. Now, suppose, next we have to prove the number of incongruent solutions to this is this number D, where D is equal to AM. Now, suppose X naught is a particular solution of the linear congruence Ax congruent to B modium. Then the corresponding linear Diophantine equation Ax minus My equal to B is solvable and its solution is given by X is equal to X naught plus M by D T and Y is equal to Y naught plus A by D T. So this is the result that we studied earlier in solving a linear Diophantine equation. If the GCD of AM divides B, it is solvable, and the solution, general solution, is given by X is equal to X naught plus M by dt. X is equal to X naught plus M by dt and Y is equal to Y naught plus A by dt, where D is equal to AM. Now, where this X naught is actually a particular solution. Now, to find the number of incongruent solution, suppose we have another solution, or we have two different solutions, suppose x1 and x2, where x1 is given by x naught plus M by d t1 and y1 is x2 is given by x naught plus M by d t2 are two different solutions or values of x satisfy X congruent to B modium. If they belong to the same class, that means if x1 is congruent to x2 modium, then we have x naught plus M by d t1 is congruent to x naught plus M by d t2 modium. That is, M by d t1 is congruent to M by d T2 Modium by subtracting x0 from both sides. But we know m by d actually divides m. That is, the GCD of m by d and m is m by d. And therefore, this congruent relation gives you that T1 congruent to T2 mod m divided by m by d. That is T2 congruent to mod d. So if x1 and x2 are two solutions such that they belong to the same congruent class, then T1 is congruent to T2 mod d. And this is obtained from the result that if AC congruent to BC mod m, then dividing by C, we know it is A is congruent to B mod m by d, where this d is GCD of A m. So from that result only we get this T1 congruent to T2 mod d. That is, if and only if T1 and T2 belong to the same congruence class modulo d. So x1 and x2 belong to the same congruence class modulo m if it is a solution to that, then T1 and T2 belong to the congruent class modulo d. So in other words, if they are incongruent, then T1 is not congruent to T2 modulo m. So this indicates that the solution x1 and x2 belong to two different equivalence class mode, congruence class modulo m, if this T1 and T2 belong to two distinct congruent class modulo d. And therefore, we can say that x equal to x0 plus m by d t is incongruent for various values of t such that 0 less than or equal to t less than or equal to d, because such a, if you take the congruence class modulo d, there are d number of different equivalence congruence classes. For T1, T2 like that, 0 less than or equal to t less than or equal to d, x is equal to x0 plus m by dt is a solution to the linear congruence Ax congruent to B mod m. Therefore, Ax congruent to B mod m, the linear congruence, has D incongruent solutions. They are different. x1 and x2 belong to two different equivalence classes. T1 and T2 belong to two different congruence class modulo D. So many D such equivalence classes are there, congruence classes are there for modulo D. And therefore, Ax congruent to B mod m has D number of incongruent solutions. Incongruent solutions. And there is a corollary to this theorem. If for any congruence relation A is congruent to B mod m, suppose AM equal to 1, that is A and M are relatively prime. In such case, here D is 1, using the above theorem, D is 1, and therefore there is only one solution, incongruent solution, to Ax congruent to B mod m. So, for linear congruence, Ax congruent to B mod m, in case AM equal to 1 or A and M are relatively prime, then this linear congruence has only one incongruent solution. Now we will see an example to determine if the congruence 8x congruent to 10 mod 6, similarly 2x congruent to 3 mod 4, 4x congruent to 7 mod 5 are solvable or not. If at all solvable, how many incongruent solutions do they have? So let us take the first example, 8x congruent to 10 mod 6. This linear congruence, A is 8 here, M is 6, B is 10. Calculate first D, which is the GCD of A and M. That is GCD of 8 and 6, which is 2. And we can see that 2 clearly divides 10. That is D divides B. By the theorem, therefore we have the linear congruence has solutions, or it is solvable. And the number of incongruent solutions is this D, that is 2. So the linear congruence is solvable and has 2 incongruent solutions. 2 incongruent solutions. Now the second example is 2x congruent to 3 mod 4. Here A is equal to 2, B is equal to 3, M is equal to 4. Calculate D, which is GCD of AM, GCD of 2, 4, which is 2. But 2 does not divide 3. That means here D does not divide M. Hence, the linear congruence 2x congruent to 3 mod 4 has no solution. Has no solution. Now the third example is 4x congruent to 7 mod 5. 4x congruent to 7 mod 5. Here A is 4, B is 7, M is 5. Calculating D, which is AM, that is 4, 5, which is 1. Clearly, D, which is 1, divides 7. And therefore, 4x congruent to 7 mod 5 has one incongruent solution, that is, has a unique solution. We can say as one incongruent solution. So in this problem we are not finding what is the solution, we just find does it have a solution, or if so, how many solutions it has got. Now let us take a problem of finding solutions to a linear congruence. The problem is solve the congruence 12x congruent to 48 mod 80. Here A is 12, B is 48, M is 80. First let us see how many incongruent solutions it has. D equal to GCD of AM, which is GCD of 12 and 18, which is 6. Clearly D, that is 6, divides B, 48, and therefore it has 6 incongruent solutions. Now to find the incongruent solutions. Earlier we saw, from the previous theorem we saw, the general solution to the linear congruence Ax congruent to B modium is obtained by x is equal to x naught plus m by d t, where 0 less than or equal to t less than or equal to d, where x naught is a particular solution and d is GCD of A m. Here d is 6, and therefore if x naught is a particular solution, so that we will find later, the general solution is given by x is equal to x naught plus m by d t, which is equal to x naught plus m, it is 18 by d is 6 t, where 0 less than or equal to t less than or equal to 6. That is, it is of the form x naught plus 3t, 0 less than or equal to t less than or equal to 6. So a general solution of this linear congruence is of the form x naught plus 3t, where x naught is a particular solution. Now by some inspection, the relation is 12x congruent to 48 mod 18. Putting x naught is equal to 1, you can see that 12 into 1 is clearly congruent to 48 mod 18. 12 into 1 is 12, 12 minus 48 is minus 36, is clearly a multiple of 18. That means x is equal to 1 is a solution to 12x congruent to 48 mod 18. So taking x naught is equal to 1, the general solution you can put it in the form 1 plus 3t, where 0 less than or equal to t less than or equal to 6. That is, the various solutions of this incongruent solutions of the given linear congruence are 1, 4, 7, 10, 13 and 16, obtained from 1 plus 3t for the values t starting from 0 to 6. Now let us solve Mahavira's puzzle that was discussed in previous chapter by using linear congruence. The problem is this: 23 travelers entered a beautiful forest where they found 63 bunches of plantains and 7 single fruits, and they divided those among them equally, and we have to find the number of fruits in each bunch. So there are 23 travelers are there. They saw 63 bunches of plantains and together with the single 7 single fruits, and they divided equally among these 23 people. If that case, what is the number of fruits in each bunch? That is we have to find. Suppose on each bunch there are X plantains. So totally there are 63 X plus another 7 single fruits is there, 7. and that is divided among 23 travelers, and suppose each traveler has got y number of plane days, so makes 23y. So actually we have to solve 63x minus 23y equal to 7 minus 7, this linear Diophantine equation. So in order to solve a linear Diophantine equation, we are actually solving the corresponding linear congruence. See here. This linear Diophantine equation generates two linear congruences. One is 63x congruent to minus 7 mod 23. This can be written this way, or minus 23y congruent to minus 7 mod 63. In one of these ways you can write this linear Diophantine equation. That is why this linear Diophantine equation generates or makes two linear congruences like this, and 63x congruent to minus 7 mod 23 and minus 23y congruent to minus 7 mod 63. Now 63x congruent to minus 7 mod 23 means, from this you can write as minus 6x congruent to minus 7 mod 23. Because 63 minus 6 is 63, x is congruent to actually minus 6 mod 23. Or in other words, 63x congruent to minus 7 mod 23, you can write as 69x minus 6x congruent to minus 7 mod 23. And 69x is actually a multiple of 23, and therefore we have minus 6 congruent to minus 7 mod 23. So 63x congruent to minus 7 mod 23 is reduced to minus 6x congruent to minus 7 mod 23. That is multiplying by minus 1, 6x congruent to 7 mod 23. Now this is a linear congruence in the form Ax congruent to B modium, and it is solvable if AM divides B. Here 623, A is 6 here, B is 7, M is 23, AM, that is D equal to AM is equal to 6, 23 equal to 1, clearly divides 7, therefore there is an incongruent solution, one incongruent solution for 6s congruent to 7 mod 23. You take this one, multiplying both sides by 4. 4 into 6x is congruent to 4 into 7 mod 23. That is 24x congruent to 28 mod 23. But 24x you can write as 23x plus x congruent to 28 mod 23. 23x is clearly a multiple of 23, so it is x congruent to 28 mod 23. And 28 again you can write as 23 plus 5 mod 23. 23 plus 5. Mod 23. Therefore, it is congruent to 5 mod 23. X is congruent to 5 mod 23. So, the general solution, X is in the form 5 plus 23 t. 5 plus 23 t. Similarly, we can calculate y, or by substituting, suppose this is the given equation, we have 63x plus y is equal to 23y. In the place of x, we substitute 5 plus 23t. So substituting x is equal to 5 plus 23t in A, we get 63 into 5 plus 23t plus 7 equal to 23y, which gives you y is equal to 14 plus 63t. Hence, the solutions to Mahavira's puzzle are x is equal to 5 plus 23t, y is equal to 14 plus 63t, where t is any arbitrary integer for any t in set. If you take some t is equal to 1, you get x is equal to 5 plus 23 into 1, which is 28, and y is equal to 14 plus 63 into 1. 63 plus 14 is 77. 77. So all the bunches, if it has 28 bananas, plantains, then each one of them will get 77 bananas each. It has actually infinitely many solutions.